Good evening once more, everyone, and I'm happy for us to continue from where we have stopped. Welcome, everyone. To start with, our usual way of starting our class is to begin by asking if there are any questions from previous class, or if there's anything you would want to add from previous class. If there are none, we can just proceed with what we have from today's class. Are there any questions from previous class? Okay, that's silent. With that silence, I'll take it that everyone has concrete knowledge based on what we have discussed from last class. So will someone just give us a quick revision of last class and then we proceed from there, please? Anyone willing to give us a quick summary of last class? Oh, we've got Divine. Okay. Divine, you can go ahead.
Okay, yesterday we talked about the stellar Soroban integration. So we first of all talked about smart contracts, and the we got an introduction into the Soroban platform, which is written in Rust. And we talked about how we write our smart contract using the Soroban platform. And we talked about key features of the Soroban platform, which is the secure execution, I think, and scalability, and so on. We also talked about how the Soroban platform, how the code is written, and then it is compiled into WASM. That's the WebAssembly integration, which is then uh, put in the Stellar core. So mostly the code we write, the smart contract we write, is compiled to WASM, and then it is then put into the Stellar
Deployed.
blockchain. Deployed, yes, thank you. That's what I want to say. Deployed on the Stellar blockchain. So we also talked about the benefits of using WASM, and we talked about high performance, security, and then that it is not language agnostic. That means you can write in different languages. So I think that was where we stopped yesterday.
Thank you very much, Divine. That was excellent. Excellent review. Anyone want to add something before we proceed? Anyone want to add anything? Okay, since no one is adding something, let's proceed with today's class. So just like Divine made mention of, we started by introducing what smart contracts are in general. We spoke about smart contracts on different blockchains. Then we streamlined it down to smart contracts on the Stellar blockchain. And then we spoke about how the smart contract is compiled to WASM and it is then deployed to the Stellar ledger. And from there, interaction happens. So today we would continue by talking about, we continue by talking about contract installation process. What are the steps? Steps to writing and compiling a smart contract. So a developer writes the smart contract code in their preferred language. In our case, our preferred language definitely would be Soroban, that is Rust, you get. The written code is then compiled into WebAssembly bytecode, creating a binary executable file that can be deployed on the Stellar network, creating a contract data ledger entry. Once compiled, the WASM bytecode is uploaded to the Stellar network. A contract data ledger entry is created to store the binary data of the smart contract. This entry includes a unique identifier, which is the hash of the executable file. What are we trying to say? We are trying to say that the moment your smart contract has been created, it is compiled, it is then deployed. The moment that smart contract WASM bytecode is deployed, a contract data ledger entry is created. And this contract data ledger entry, we are still going to talk more about what exactly it is. But it is created, and this now stores that binary data, which is the byte code of that smart contract on the ledger. And once it is created, it creates a unique identifier. Someone was asking me how we can identify a smart contract that has been deployed. Yes, this was what I was trying to explain from yesterday's class. That once you create your smart contract, it creates a unique identifier. And that unique identifier is literally the hash of the executable file. So that means that once you deploy your smart contract, you get an address. That address is a unique identifier that you use to identify your smart contract. So storing binary data and unique identifier. So the hash of the executable file serves as a unique identifier, ensuring that each smart contract is distinct. So each of the, if I deploy my smart contract, Divine deploys his own smart contract, even though Divine's code is the same thing, it's exact replica of my, imagine I went to steal Divine code. I went to just clone Divine's code base, his smart contract. So everything is just the same. And then I went to deploy that smart contract. Even though Divine has deployed the same smart contract, what ensures that the binary code of Divine and mine is different is the unique identifier. So you can have 2, 3, 4 more smart contracts that are the same, but then what differentiates them would be this unique identifier. And as time goes on, we will even talk about what we call factory contract, that is creating contracts from this unique identifier. We would also see how the creation of these different initialization of these new smart contracts from this unique identifier is also separated. And we'll still talk about how the storage of these smart contracts are also separated. So look forward to that. Moving on, the binary executable file is stored separately from the deployed contract instance, and allowing for reuse and efficient management of smart contract code on the network. So that is exactly what we've just explained, that this executable file is literally stored separately from the deployed contract instance. So what are we trying to say? We are trying to say that when you deploy the smart contract, you have this binary executable code. It is stored there. Then from this binary executable code, you now initialize an instance from that deployed contract. So it allows you to do what we call factory contracts. Still going to talk more about that. Contract invocation and execution. How transactions invoke smart contracts. So transactions on the Stellar network can actually include operations that invoke smart contract function. So that means that when you write a smart contract, you can interact with this smart contract by calling the functions that are inside that binary code that has been deployed to the ledger. So when a transaction attempts to call a smart contract function, that WASM bytecode for that contract is retrieved from the ledger. And so it then interacts with it as if you are, interacting, you are calling functions from your smart contract, basically. Retrieving WASM bytecode from the ledger. The network fetches the stored WASM bytecode based on the unique identifier associated with the smart contract. And this ensures the correct version of the smart contract is executed. Like I said, imagine that Divine's code base I, copied, I cloned. I could have changed something different again from that code base and I deploy again. It will definitely have a different unique identifier. So imagine, all I'm just trying to say is that if you deploy the same smart contract 20 times, the smart contract will keep having different unique identifier, basically. And so it's the unique identifier you will then use to interact with that smart contract. So you get, in a simple sense, you can think of it like mapping. So that unique identifier is mapped to your WASM bytecode on the ledger. So when you want to interact with that smart contract, all you have to do is to use the unique identifier and then you call your functions using that unique identifier. Secure isolated runtime virtual machine. A secure isolated runtime virtual machine is instantiated to execute the WASM bytecode. And what are we trying to say? Starting from when I've been talking about the difference between Bitcoin and Ethereum, I was talking about an executable environment. And that is exactly what we are now digging about. When you want to interact with your smart contract, a virtual machine is instantiated, and this virtual machine is what executes the WASM bytecode of your smart contract. And then this virtual machine environment also ensures that this smart contract runs securely with no risk of affecting other operations on the network. Because imagine you are calling your own smart contract and someone else is also calling his own smart contract simultaneously. What ensures that there are no clashes or there is no interference is this isolated runtime virtual machine where your own WASM bytecode is being executed. So once the execution is complete, the virtual machine exits and it maintains the integrity and the security of the blockchain. Are there any questions before we proceed? Can we get a thumbs up to show that, okay, we can proceed and there are no questions? Okay, great. Tez have a question.
Yeah, just wanted to check for the time virtual environment. So does that mean if you run transactions that don't include smart contracts on Stellar, will they execute faster than transactions that do include smart contracts? I just want to check if there's a difference in the time for execution because of that extra call to the virtual environment.
Exactly. Now, let me ask you a question to answer your question before you unmute. Imagine we have a smart contract that calls two smart contracts. Now, we have a function in a smart contract that calls two smart contracts. We are going to talk about that later on. But based on this question you're asking, I want to believe that you have knowledge on smart contract. Now, you also have another function that does not call any smart contract. Between these two functions, which one do you think would take more time and would take more gas?
The one that calls the smart contract.
The ones that calls multiple smart contract, or the ones that calls that doesn't call any smart contract, it just interacts with its own storage. Which one do you think would take more time for execution?
The multiple smart contracts.
The answer to that is no. The lesser work, it's just like saying the lesser work you do, the lesser time it takes. It's a simple thing. It's more like the work is proportional to the time. Work done is proportional to the time. You get, when there are lesser executions, lesser lines of code in a function, it takes lesser time to execute. And when there are more interactions, just one function calling 2-3 smart contracts simultaneously for interaction, that's intra-contract interaction, it takes more time. So now compare it with just you sending Lumen to a person. You are not executing any smart contracts. Definitely that would be faster than you executing smart contracts. I don't know if that makes sense to you.
Right. Yeah, no, I understand.
Yeah. Thank you for that question. Contract instances. Explanation of contract instances. After the executable bytecode is installed on the Stellar network, contract instances can be deployed. And these instances reference the install bytecode but function independently. What am I trying to say? What I'm trying to say is that the moment, in fact, I'm going to, give me a second. I think I'm going to draw this to explain what I'm trying to say. Give me a second. Let me share my screen. Basically draw this. I like drawing to make the point clearer. So can you see, can you see my screen? Okay, let me reshare and reshare all. Okay, can everyone see my screen now? Oh no. Okay. Is there a
No,
reason why?
sir.
Yeah. I can see you can't see my screen. I'm just trying to figure out why I'm not being able to share all of my screen. Okay, that's fine. That's fine. I guess I won't be able to show what I want to show the way I want to show it. So let me use something else. Let's use something else to illustrate this. So we're going to use Escal Draw to illustrate this. I think the reason is because I've not shut down my system for a very long time. So I can't even share with this. Okay, I'm sure everyone can see the whiteboard on my screen, right? Okay. So we are going to illustrate it using this whiteboard. Okay, is Keisha's hand up?
Sir, do you mind increasing the size? We can't see it quite clearly.
Oh, no problem.
See you now.
I've not even started drawing anything, but yeah, you can see it better now, right? Okay. Okay, we are going to use this as an illustration. So imagine this is my hand is so not straight, but you'd have to manage my hand. So I'm going to use this as an example. Imagine this is the ledger. Now, imagine you have, let me finish drawing what I'm drawing, then I would explain it. Okay, and then don't mind my drawing. No. Just let me finish drawing and then I'll explain where I'm getting at. Okay, let's stop here and then we talk about the explanation. So imagine this big box is the Stellar ledger. That's the Stellar core, the full blockchain altogether. Now, the moment you finish compiling your smart contract, your Wasm bytecode is created. Imagine this box as the Wasm bytecode. Now, when this Wasm bytecode is created, it gives you an hash. It gives you an hash. Now, that hash is what gives you opportunity to now create contract instances. So now you can now create different contract instance from just one Wasm bytecode. So just this Wasm bytecode can now have, you can now create a contract instance 1, contract instance 2, 3, and on and on and on and on like that. So each of these contract instances, they now have individual storage. So each of these contract instances have their individual storage, but all of them, whenever they want to call a particular function, all of them will still refer to this original Wasm bytecode. So that means that imagine you are creating a kind of implementation whereby you are having about 5 different smart contracts doing different things. For example, let's use the example of a popular illustration, a pool. Now, you know that in a pool, you have a pool that's been, you have a factory that deploys so many pools. Now, this factory that deploys all of these pools could serve as this one, whereby each of the pool are now individual smart contracts of their own. with the same implementation. But then whenever you want, each of these smart contracts want to call a function, all of them still refer to this wasm bytecode to call that particular function. And then they then store their own implementation based on the storage. And each of them don't affect each of them. Does that make sense? Okay.
Hi, Mr. Ayo. Okay, I am kind of a bit of confused there for a sec, but are you trying to say to me that for all those pools, it's like having one, like a template of a smart contract, right? Where you can implement on all these pools, but obviously in different forms, but using one smart contract. Is that what you say?
Yes. And then you can now initialize, instantiate instances of this smart contract. So each of these instances will now have their own separate storage.
Oh, okay. All right. All right.
Yeah.
Cool. Thank you.
So for those coming from the EVM background, you can think of this like a factory contract. A factory contract that creates new contracts. There are different ways of creating new contracts in the EVM. You have minimum proxy, you have create2, you have create, and on like that. So you can think of it as something like that, like a factory contract. But each of these contracts now have their own individual storage. So, okay, great. So let's go back to our slide and continue. Let me share a slide now. So that's basically the independent functioning of multiple instances. So contract instances basically operate independently despite using the same bytecode. And this allows for scalable and flexible deployment of smart contracts. So imagine you have a smart contract that you want to create for hospitals, keeping hospital records and all of that. You know, you could have about so many hospitals all around, and then you could just create that one contract and deploy it, and then you create instances for different hospitals, and then each hospital, they are able to operate based on the same functionality, but the instances of this smart contract having different storage and one not affecting the other. So that's just like a vivid explanation of what we are talking about. Now, you heard me saying contract storage, contract storage. Now we've gotten to contract storage. Contract storage overview, different types of contract storage. Smart contracts on Stellar can utilize different types of storage to maintain their state and data. The major types of storage includes temporary storage, permanent storage, and instant storage. So there are different types of storage. I'm sure from one class back then, when we were talking about renting storage, paying lumens to rent storage and all of that, we spoke about this. And I made mention that in future class, we are going to talk more about it. And here we are talking about it. So there are different types of storage. You definitely know that temporary storage would not last long, just like the name connotes. Permanent storage, definitely longer than temporary storage. Instant storage, not as long as permanent storage. So there are different situations where you might need temporary storage or permanent storage, and based on what you want to do. What then is the importance of storage in smart contracts? Proper storage management is crucial for functionality and efficiency of smart contracts. Different storage types cater to different needs and use case, providing flexibility for developers. And it is true. Let's remember that this implementation of temporary permanent storage is a very good thing, because at the end of the day, there are some smart contracts that we deploy, and we really don't need that smart contract to live forever. It could be that the smart contract is deployed for a particular voting session, and after this voting session is over, the whole smart contract is gone. Or it could be a smart contract that is deployed for probably airdrop, and after that airdrop session, there is no need for this smart contract. We want to remember that those people that are running the node, that are running the client, the software for this Stellar Ledger, at the end of the day, the more the smart contract deployed and the more the storage created, there is a sound I'm hearing, please. Can the person on? Okay. So, as I was saying, the more the smart contract, the more the storage that is being used. And what does this mean? When there is more storage that is being used, it means that you need to buy higher hardware for you to run that Stellar client, for you to run the Stellar core. So it makes sense basically for smart contracts that are not needed anymore to be archived. And archived smart contract would mean reduced usage of space for the people running the node. So it's a very, very good thing. And so based on what type of smart contract you are trying to build, if you build a smart contract that needs a permanent storage, and at the end of the day, you went to use temporary storage, that's a big vulnerability. The smart contract could be a smart contract that would hold so much finance, and then at the end of the day, the finance is lost based on the fact that you used a temporary storage instead of a permanent storage. I'm sure we have been talking about this. We would see how we can implement a temporary storage and a permanent storage when we begin writing the Soroban smart contract itself. Temporary storage. Before we move on to defining all of this storage and the use case for each of them, is there any question based on what I've just explained? Is there any question? Okay. The silence, you take that silence as no question. So we would proceed. Temporary storage. I mean, temporary storage comes from the name temporary, and it's literally okay. I'm seeing a chat. Okay. Temporary storage, it basically comes for the name temporary. And when we say something is temporary, that means it doesn't live long. So temporary storage is used for data that is short-lived and does not need to be preserved permanently. And to be very honest, it's the most cost-effective storage option on the Stellar network, because as long as it's not taking so much, it's not taking space for a very long time, then the amount of lumens you pay for that storage when deploying, it's not as much as what you will pay for something that would take a very long time. So I think you should put this at the back of your mind, that also there's no need for you to use permanent when you need to use temporary, because you get to pay more for permanent when you know what you are doing would not live long, and it will be dumped after it has been used. So that also creates cost effectiveness when you are dealing with storage. For the fee structure, temporary storage incurs the lowest fee compared to other storage type, and it makes sense. This is because it deals for storing data that does not need to be retained for a very long time, and that makes sense basically, no questions. Uses for temporary storage is suitable for time-bound data such as price oracles, signatures, or any data that can be easily recreated. When I was talking, I made mention of something like airdrop. So you could create a smart contract that checks for signatures and marker routes, basically for airdrop. And once it has been used, the smart contract becomes useless. And you can use the temporary storage for this kind of case. It's also ideal for scenarios where the data is needed for a short period and can be deleted once its purpose is fulfilled. So that's basically it for temporary storage. So we're moving on to permanent storage. Just like the name denotes, permanent storage is used for data that needs to be retained for longer period of time. And it's crucial for smart contract functionality. So a smart contract whereby you know that you need the data to live for a very long time. You're opting for permanent storage. And so it's normal for something like that to be expensive than the one that would not last for long. So it's more like you're buying a storage. Imagine you're buying a memory card. The one that will last for 5 years and the one that will last for 6 months. Which one will be much expensive? So you can think of it like that. So the permanent storage will definitely be more expensive than the temporary storage. What's the fee structure? Permanent structure storage incurs higher fees compared to the temporary storage, reflecting its importance and durability. Use case for permanent storage is suitable for storing user data that cannot be temporary, such as balances, user profile, or any critical contract data that must be retained. You see, that first one, balances, is usually one of the most important reasons why you need to use a permanent storage. Imagine you are creating a contract that has to do with staking. And now you know that your staking contracts will probably go through a cliff period, and after the cliff period, then users can then begin to, get their stake gradually. And at the end of the day, you now use the temporary storage, and then the user balance on the smart contract is then archived and wiped. At that particular point, users will hold your hand for their money because you no longer have access to the balances. So in this particular case, it's always wise to use the permanent storage. Another one is user profile. You know, a user is not going to leave. And for a user that wants to use your application, your DApp, you need to keep the user profile for a long time. Imagine you opt in for temporary storage and then the user loses his profile based on the fact that the contract has been archived and can no longer be accessed. It won't be wise to do such a thing. It's also ideal for applications where data integrity and longevity are crucial. Instant storage. Instant storage is a specialized form of permanent storage tied to a life cycle of the contract instance. So it functions similarly to permanent storage, but it has a limited amount of storage available. So the instant storage, like you would hear instance, it comes from instantiating a contract you get. So when you instantiate a contract, you could use this kind of specialized storage, which is instant storage, that is tied to the life cycle of that contract instance. And so when the contract instance is over, then the lifetime of that storage is also over. So the instant storage incurs the same fee as the persistent storage, and it reflects the importance of maintaining the contract instance state throughout its life cycle. So the contract instance state is what should be maintained because this is closely tied to the instance storage of the code itself that is deployed on the ledger. Use case for instance storage, suitable for storing shared contract states such as admin account, contract metadata, and other essential data. Moving on. So when I was talking about, okay, Silvanus.
Please, can you repeat instant storage?
Okay. So we said that instant storage is basically closely tied to persistent storage. That is, it looks like persistent storage, but then its own life cycle is connected to the instance of the smart contract that is being instantiated. So basically, when the smart contract that is being instantiated is created, the lifetime of that smart contract instance is closely tied to the lifetime of that contract itself. That is the wasn't bytecode itself. So that means that the moment the lifetime of this contract instance is over, that is, the life cycle is over, then automatically the wasn't bytecode is also gone and it is archived. So instead, it is dependent on the lifetime of the instance of the contract, not the wasn't bytecode itself. So does that make sense?
Yes, thank you.
Okay, great. Does anyone have any question before we proceed? Apart from Sylvanus. Okay. So operations and transaction. Before we start talking about operations and transactions, I'm going to share my screen and take us back to the Stellar scan where I showed some operations inside of the ledger. So let me quickly open that up and I will share my screen. Okay. Okay. Your hands are up. You can unmute and speak.
I know maybe I could be asking just something that probably it's not in the scope. Is it possible for you to show us probably like a live smart contract?
You are definitely going to get there.
Oh, okay, perfect.
Don't worry. It's a 3-month program.
Okay. Now I was just checking, brother.
Yes.
Are
You're
we?
going to get there. And in fact, don't tell me you are tired of writing smart contracts when we get there. Because you write a whole lot of smart contracts.
No, Chief. I'm looking forward to it.
Okay, great. You see, I always keep repeating this because most times you could feel that, oh, we are talking so much about the intricate parts of the whole Stellar network, and you meet an average individual. I can write smart contract, but when you ask him certain things about smart contract, it becomes a problem. I would not want that to be our own case. That's why I'm trying my best to ensure that every single thing is being understood before we start writing the code. And so that's why when you have a problem with your smart contract, you can think and understand why your smart contract is behaving in certain ways. So imagine we just started writing smart contract and then created a contract instance, and I never explained how that worked, but I just showed that, okay, contract instance, I've created it and this is it. It won't be too nice when you don't have the background knowledge of it. So that's why I'm trying to do all of that. So let me share my screen and show what I was about to show. So if you remember from our class when we were talking, let me increase this so more people can see it basically. When we are talking about the Stellar ledger, I spoke about the different components and then I didn't touch operations. I mentioned that I was going to touch operations later on. But I didn't touch operations and transaction. So what are operations and transactions? So can you see this? From your screen, you can see create accounts. This is an operation type. You can see set option. This is an operation type. You can see change trust. This is an operation type. All of these are operation types. But then, what exactly are these operations? Let's go back to our slide and then talk about it. So right now, I'll be sharing my slide on operations and transactions. What are operations? Operations are individual commands that modifies the ledger. They are the building blocks of transaction on the Stellar network. I wish I could share all of my screens simultaneously so I could be relating the scan and the transactions on this scan in comparison to how all the operations are being done. Well, let's just continue. So let's say you want to modify the ledger. What do we mean modifying the ledger? We mean adding transaction to the ledger. So adding transaction includes operating certain commands. And these commands are literally what modifies the ledger. So let's say you send you're sending certain transaction, and the transaction has to do with, for example, one of the type of operation I made mention of is create account. So this person literally created a new account. Can you remember when I was talking about how much it is to create a new account on the Stellar network, how small and minute the money is that for you to create it? So that is literally one of the operations on the Stellar network to modify the system. So an account has been created, and so it's more like a transaction that is being sent to the Stellar network. Another one has to do with operations that has to do with payments. Some payment operation, you use the payment hub for this particular operation. Other operations could be invoking your smart contract function. So let's say you're trying to interact with your smart contract, and this smart contract, you are creating a write call to the smart contract that modifies the storage of your smart contract. That is also a different operation. So examples of operation, we have payment operation, create account operation, change trust operation, invoke host function operation. So there are so many operations. Give me a second. I'm going to show from the Stellar documentation how many operations there are for you to know how much there are when it comes to operations on the Stellar network. So for every single transaction that is being sent on the Stellar network, an operation is being used. So let me share my screen on that. So stop presenting and presenting the Stellar documentation. Okay, so I'm going to increase this so it's clearer. Operations and transactions. So we are going to go into operations. So there are so many operations inside of the Stellar network, and all of these operations are literally what actually modifies the Stellar ledger. So let's go to the list of operations. Here are the list of operations. We have the create account operation. We have the payment operation. This is still under the payment operation. All of these. Still part street receive, still an operation. The list goes on. We have manage and buy offer operation. We have manage sell offer operation. Create passive sell offer operation, set options of operation, change trust operation. What does it do? It creates, update, or delete a trust line. We have allow trust. All of these are different operations on the Stellar network. So you can think of what you are working on, and you are trying to send a transaction using the Stellar SDK. You can basically create certain operation. For example, this one is revoke sponsorship. Sponsoring accounts can remove or transfer sponsors of existing ledger entries and signer. This is another type of operation. So if you go back to that scan, you see that the different transactions literally have the different operations inside of it. You will notice that most of it has been a payment operation, and others allow trust, clawback, and set operation. So you can go in your own leisure time to go about to check all of these operations based on what you want to do. This one is liquidity pool deposit operation. So there are a whole lot of operations that you can check. So going back to a slide, You notice that we were talking about transactions and operations. This is because two of them are closely tied. For every single transaction you send to the ledger, this is what modifies the state of the ledger. And each of these transactions, literally an operation is inside of it. So it could be whether to create an account, operation, payment, and on with those operations. Threshold categories and signature weights. Operations actually fall into three threshold categories. We have the low operation, medium operation, or high operation. Each of these threshold category has a weight between 0 to 255, which determines the required signature weight for the operation to be accepted. So this means that when you are sending a transaction, that transaction could include so many operations, and these operations could now fall into whether a low or a medium type of operation or even a high operation. And so there is a threshold for these categories of operation, and this threshold is between 0 and 255 for this operation. So it's important that while you are sending your transaction, you understand the threshold for the operation to be accepted, basically. Transactions structure. Component of a Stellar transaction. Transaction on Stellar consists of a source account, a sequence number, and a list of operations, and an optional memo. So that means that when you are creating a transaction, there are things you are going to see inside of that transaction. The source account. The source account is literally the account that initiates that transaction. So let's say I'm trying to invoke a function from a smart contract. Remember that I said that for you to invoke a function from a smart contract or interact with a smart contract, you need to have an account that would create this invocation. So the account is the source account that created that transaction. So that should be found in the in the Stellar transaction. Another one is the sequence number. I was talking about the sequence number when I was giving an illustration in time past of what we call norms. So when you're sending a transaction, each transaction have its own sequence number, and each sequence number must be used. That is a transaction. Imagine I'll basically use the same illustration I used from previous class when I was saying, imagine we have sequence number 5 and we have sequence number 4. If you send both transactions simultaneously, sequence number 4 has to be picked over sequence number 5 for the transaction. So that ensures that you don't go about what we call double spending. So there's a sequence number for it. Then there's a list of operations, which we've just explained the different types of operation you can have in the Stellar network. Also, we have optional memo. So the optional memo is a place where you could add more like a simple note on the transaction that you are trying to send. So the source account initiates the transaction and signs it to authorize the included operation. And so that's literally what it's all about. So whoever is trying to interact with a smart contract, an account has to sign the smart contract, that has to sign the transaction and initiate the invocation or the interaction that the smart contract and the account is trying to do. So it basically have to have a source. So that means that when you are deploying your smart contract, you need to create an account to initialize that transaction. So every transaction on the chain, on the blockchain, it has to go through an account. Source account and sequence number. The source account is the account from which the transaction originates, yes, just like I've explained. The sequence number ensures that the transactions are processed in correct order, just like I explained. So sequence number 3 transaction must go before sequence number 4 transaction. So that means that even though you send the transaction simultaneously, it doesn't mean that the 4th one will go before the 3rd one. So the 3rd one has to go before the 4th one. List of operations. A transaction can include multiple operations allowing for complex multi-step processes to be executed within a single transaction. I think it was Tess that I was asking about a smart contract that literally interacts with about two smart contracts, a function inside a smart contract interacting with functions inside two different smart contracts, and just one that just, you know, update its own state. That which one would take more or more time to process and more time to be executed, or more gas to be to execute the contract. This is a vivid example of it. When a transaction includes so many operations, then in that particular case, it would involve so many processes to be executed in that single transaction. Imagine you have a function inside a smart contract that calls another function that updates the state of another contract, and in that process, after updating the state of that contract, it then invokes another contract and even creates a new smart contract, probably like instantiating another smart contract simultaneously, all done inside of that single function. This would create multi-step processes, and definitely to take more time for these to execute than just a function that is, you know, updating its own state without having so many multiple steps inside of it. The optional memo feed. The memo feed literally allows for additional information to be included with the transaction, such as reference number or a message. So just like you've heard, it is optional. Optional means that you necessarily don't have to fill it. You can leave it empty. But if you want to fill it, it could be more like a message that you're attaching, or a reference number that you're attaching to that transaction. So probably you want to send Lumen from one person to another, and you then just add a memo to it, and the memo saying thank you or something like that. You know, it could just be added to the transaction, more like the reference number. Transaction envelope and metadata. Before we proceed, I know we've spoken about so much on transaction and operations. Are there any questions at this point before we proceed? Can we get thumbs up to show that? Okay.
Hi, there's no question. It's just to go through the video again. We appreciate if we can have the videos available. I think.
Yeah, you definitely have the video available. You have the video available. Okay. Great that everyone is on the same side. Okay. Transaction envelope and metadata. The purpose of the transaction envelope literally encapsulates all the components of a transaction, ensuring that they are transmitted and processed together. It includes the source account, sequence number, operations, memo, and signature. What are we trying to talk about? All the things we have mentioned as what is included inside of a transaction. You can think of it having more like an envelope that literally encapsulates all of it together. And all of it being encapsulated together literally shows that anyone is not skipped or anyone is not left out, because we mentioned that a single transaction could have so many operations inside of it. So to ensure that all these operations are executed, all of these has to be encapsulated together inside of the transaction envelope, basically. So I don't know, I think I should look for a transaction that has so many operations. So I think, let me share my screen, and we look for a transaction that has so many operations, and we use this to explain the transaction envelope. So we are going to go to one source. You know, it's beautiful when we have something like this that can give us access to the Stellar chain. So none of us on this call is literally running the client. So the only way we can have access to the information is literally through this scan. So we are going to look at the ledger. This is this ledger sequence, and these are the transactions inside of this ledger. So inside of this transaction, notice this one. This particular transaction has 12 operations. Did you notice that? It has 12 operations. And so let's open it and see all the operations inside of it. So inside of it, look at the operations is that it had this one. Oh, I shouldn't have clicked on it. Manage by offer, manage, all of this inside of just a single transaction. All of this inside a single transaction. And you notice that it is actually inside a single transaction because it literally have the same transaction hash. Notice that all of it have the same transaction hash. So it's inside a single transaction. So this is an example of a transaction that could have more than one operation. Look at this one. This one has just one operation inside of it. And if you look at the operation is managed by offer. It's just a single operation inside of it. But compared, now let's be logical. Let's look at this one that has about 12 operations inside of it. Did you notice the gas fee that this one took? This one took about 0.0012 gas fee. But compared to it that had just one operation, it took 0.00001 gas fee. So that literally goes on to explain that the more operations, the more execution, the more time taken, and also what? The more gas fee that is being used. So that is more like a summary on what we have spoken about, how a multi execution of operations inside of one transaction. So now let's talk about all of the envelope. Now look at the envelope. So we can literally call this the envelope. Why can we call all of this the envelope? This is because this is the source account that initialized it. What else do we have inside of it? We have the operations. Here are the operations. What else do we have inside of the envelope? We have the sequence number. Can we find the sequence number? Let's see. Okay, can we find the sequence number? The sequence number should be up. Transaction 1, okay. Let's look for the sequence. Sorry, I clicked back and so I left the call mistakenly. Okay. So let's see the sequence number. Should be able to see. Okay, yeah. This is the ledger sequence number. So can you see the sequence? That's it. So all of this is basically encapsulated inside of the transaction. So this comes to the end of our class for today. Thank you very much, everyone. I would stop the recording now and we meet tomorrow and we complete the slides from tomorrow's class. Thank you once more, everyone.